Okay, so like I said, section 11.4, we're going to go over the equations of your non-standard conics. So that would be hyperbolas, ellipses, and parabolas. This time the center is going to be at some place other than 0 and 0. So our generic center for all these is going to be H and K. Now, I've got, one version of the formula for an ellipse. How can you tell it's an ellipse versus a hyperbola? What do you think the big clue is? If you're looking at this going, oh, I don't know what this is going to be. What's your big clue, Jesse?
You're adding instead of subtracting the equation.
Exactly. So for an ellipse, it has to be a plus. For a hyperbola, these two things are going to be subtracted. That's good. Now I've got two different versions here. What do you think the difference is between each of these versions? I mean, how come I've got two different versions of the graph of a hyperbola? What difference does it make? What difference could it make? Well, in the one case, I've got an x squared term that's first. In the other case, I've got a y squared term that's first. How's that going to affect the graph of the hyperbola?
The major axis.
Go ahead, Julian.
Are we doing?
It's all right.
Go ahead.
The major axis is gonna be changed depending on which comes out first.
All right. So up here, if one of these is bigger than the other one, and they have to be an ellipse, then the longer one's going to be your major axis. So, but here, what I think you're getting at is that this one's going to open left and right. Whereas this one, which way is this one going to open? Yeah, opens up and down. All right, so that's the big difference between these two. And last but not least, down here you've got two different versions of the equation of a parabola. Both of these have a vertex at H and K. But there is a little bit more that we need to remember about this. And that is, these are going to open in different directions. Which way is this top one going to open? Yeah. Up and down. Up or down, I should say. What determines if it opens up and down?
The A value.
Yeah, if this is positive, it's going to open up. If it's negative, it's going to open down. This one, by contrast, is going to open left and right. Yay. All right, so those are your equations of ellipse. As a reminder, this coefficient A equals 1 over 4p, or another way to state it is P equals 1 over 4a. But what does P represent? Do you remember what P is all about? I know it's been a little while because we've been on vacation. Yeah.
It's the distance between the vertex and directrix.
And yeah, well done. Directrix. Yeah, distance between the vertex and the directrix. So, all right. Let's play around with some of these and see what this gives us. Keep in mind, although I will let you use Desmos, I am going to want exact answers. So let's take a look at the first one, which is example A. Looking like this. Let's start by putting this in more of a standard form. Typically, I'm not going to write it like this when I graph it. At least I'm not going to think of it like that. How am I going to change this, Sean?
You could write it under the 16 could go to a 4 squared, and the 9 could go to a 3 squared.
Perfect. So I'm going to write these as perfect squares. So 3 squared and 4 squared respectively. Excellent. Jacqueline, can you tell me where the center would be?
-2. Oh wait, 2 and 3.
Good, 2 and 3. You're looking for the values that make each of these binomials 0. So that would be x equal 2 and y equals 3. Perfect. So that gives us a center right here at 2 and 3. And you can see that if if you move a distance of 4 away from the center in either direction, left or right, you're going to find the vertices. Something doesn't look great, this graph, but I'm not going to worry about that. 1, 2, 3, 4. Yeah, it looks a little short for some reason. Not sure. It should be perfectly right there on, well, actually, let's figure out what point it should be on, because it looks like it's short. Now, the center is at 2 and 2, or 2 and 3. Which coordinate am I going to change to find this vertex here? Am I changing the x coordinate or the y coordinate?
The x-coordinate.
Yeah, the x coordinate. Good. So adding 4 to the x coordinate, that point would be at 6 and 3. Subtracting 4 to the x coordinate, that point would be at -2 and 3. I've also got to find the coordinates of the vertices north and south of the center. So in this case, I'll go up by 3 and down by 3. So again, you're going to be changing a coordinate. This time it's the y coordinate, so adding 3 here. Keep the x coordinate the same. Add 3 to the y coordinate. Keep the x coordinate the same. Subtract 3 from the y coordinate. There's your vertices. Nice. Now, I'm going to want the exact equations or exact numbers for the foci. You might remember some work with the foci a little while ago. We had to calculate this thing called c squared. And c squared we calculated as a squared minus b squared, or b squared minus a squared. You just got to subtract these in such an order that it's some positive number. In this case, that's going to be 4 squared minus 3 squared, or 7. If c squared equals 7, what does c equal? Square root of 7. Beautiful. All right. But now we've got to start out at our center and move the square root of 7. Robert, which direction am I going to go that square root of 7 away from the center to find the foci? Left and right, good. So that means I'm changing which coordinate? Jason?
The x.
Yeah, changing the x coordinate. So it's going to be 2 plus the square root of 7, and keep the y coordinate the same, and 2 minus the square root of 7. Keep the y coordinate the same. That's going to be your foci. So call it F1 and F2. I don't know exactly what 2 plus the square root of 7 is going to be. So let's just do that here. Oh, 2 plus the square root of 7, about 4.6. So, all right, it's actually going to be very close to the vertex here. I'm not going to look for anything super fantastic, but if you put it, say, between -1 and 0, then I might be a little bit unhappy. So we'll call this one, that one, first one is going to be F1, this is going to be F2. Looking pretty good there. All right. How's that first one looking? Doing okay on that one? Let's try a couple more here. Next, I want to go on to example towards the end of our work here in this one, and that's example J. So I'm going all the way to the back here, I think. Yep, that one. First things first. This is a hyperbola, we know that, because there's a subtraction between these two things. So the fact that it's hyperbola goes along with the subtraction here. Well, what's its center? Oh, I'm sorry, go ahead.
-1 and 5.
Sure. -1 and 5. It's the points that make these binomials 0. -1 for x and 5 for y. Good. Ella, which way does this open? Up and down or left and right?
Left and right.
Okay. Noah, do you agree?
Yes,
Nice.
it does.
Yeah, opens left and right. That's because this term is positive, so opens left and right. Excellent, thank you both. And let's see here. I'm probably going to rewrite this as x plus 1 squared over 3 squared minus y minus 5 squared over 4 squared equals 1. And I do that so that I can start drawing some boxes. Now, I'll start with the graph of my center, which is at negative 1 and 5. So right here. And I've got to draw a couple other points. 2 of them are going to be vertices, 2 of them are going to be just points that I'm going to use to graph this. Let's see. So this is going to open left and right. That means in the x direction I'm going to have my vertices. So let's see here. How far do I have to move away from this to find my vertices? Away from the center. How far away from the center am I going to move?
Right.
3. So it's going to be negative 1 plus or minus 3 comma 5. Or in other words, for the negative case, negative 1 minus 3 is going to be negative 4 and 5. And adding there is going to be 2 and 5. So that's where my vertices are going to be. I'll put those in blue. So here, 2 and 5, and then negative 4 and 5. That'd be there. That looks good. Now I'm going to graph 2 other points here to help me with the graph of this equation. Help me with the graph of this equation. Where am I going to find those 2 other points? Do you remember? Where are we going to find? Because eventually I need to draw a rectangle around this, right? Where do I find those 2 other points? How far away from the center do I have to go to find those 2 other points? 4. So I'm going to go up 4 and down 4. So up 4 is going to put me at negative 1 and 9. And down 4 is going to put me at negative 1 and 1. So yay. Looking good there. Remember what we do next? Draw that little box going through here. So do that. Okay, let's draw some diagonals here. Now, just a little word of caution for you. When you draw the diagonals, these lines should go directly through the center. If they're off by a little bit, that's fine. But if they're off by a noticeable amount, that might mean that you went a little too far in one direction or the other when drawing your diagonals. We are going to come up with the equations of those diagonals in a minute, and I'm going to show you a cool little trick to do that. Now, this is going to open left and right. We already determined that. So, just a heads up here, that little point that I put on your x-axis, those points are going to be where the graph crosses the x-axis. So those are your x-intercepts. And I did that just to help you draw a decent graph. It comes down to here, it just touches that vertex. then it comes up here. And I hope I'm not giving anyone vertigo doing this. There, and then like that. The only thing I ask is, well, a couple things. That they just kind of touch this vertex once, that's a better looking one. And don't bounce off the asymptotes, kind of gets closer, never really bounces off of it. So, looking good there. Let's see, there's a couple more things we need to determine. The first one is the foci. So let's find the foci. And for that, I'm going to calculate c squared. But there's a difference between c squared in this one and c squared in the last one. You remember what the difference is? I know it's been a while, you're just coming back off a break. Yeah, it's a squared plus b squared. So in our case, it's going to be 3 squared plus 4 squared, which is 25. So c equals 5. So our foci are going to be at our center plus or minus 5. So -1, leave some space, 5. So this is how you're going to find your foci. It's going to be -1 plus or minus 5. -1 plus 5 is going to be 4. So I'm going to have focus at 4 and 5. -1 minus 5 is going to be -6. So -6 and 5. So we'll call that F1 and F2. So F1, 1, 2, 3, 4. So that's my F1. And then -6 is F2. Hopefully this is just kind of mostly reminder stuff with the added benefit that now we're not confined to having a center at 0 and 0. Just kind of another heads up and reminder. The length of this distance from vertex to vertex, that's your transverse axis right there in between those two. Let me pause for a second. This is a good start on this problem. But there is one last thing that I asked us to find, and that is I want the equations of these two lines. And now there's a couple ways you could get those two equations. You could look at these points and say, oh, okay, well, I got a point here and I got a point here. I got 2 points, that determines a line, and you can find the equation that way. Nothing wrong with that at all. Hopefully you remember how to do that. That would be, you'd start out with m equals y2 minus y1 over x2 minus x1, and then, you know, use this formula, y minus y1 equals m times x minus x1. So you'd use a combination of those. But I've got a better way that I'm not going to take the time to justify here, but it works. So, disclaimer, you're not going to see this in the book. I don't know of anyone else that I know of that uses this. But I figured out a long time ago, if you want the equations of the asymptotes, a cheap way to do that, an easy way to do that, is to set this equal to 0 and then solve for y. So let's see what's involved in that. So if we do that, then it's going to be x plus 1 squared over 9 minus y minus 5 squared over 16 equals 0. Okay, and let's just work towards finding that equation, finding what y equals. So the first thing I'll do is I'll move this to the other side. I'm just going to take that whole term to the other side. And what does that give me? That gives me x plus 1 squared over 9 equals y minus 5 squared over 16. And then I'm gonna multiply both sides by 16. Because I wanna get rid of the denominator on the right-hand side. So, mult by 16. So that's the second step here. And that gives me 16 times x plus 1 squared over 9 equals y minus 5 squared. Okay, I'm getting a little closer. In fact, now what I want to do is I want to take the square root of both sides. So the next step, if I take the square root, on the left-hand side I've got to take plus or minus. Plus or minus the square root of 16 times x plus 1 squared over 9 equals the square root of y minus 5 squared. And you know what, I'm going to just move on to a different page because I don't want to try and cram all this in. Now let's take it a step at a time. It's going to be plus or minus. What's the square root of 16? 4 over 3 times x plus 1 equals y minus 5. By the way, you only want the plus or minus on one side. Well, I'm almost done. What do I have to do to get y by itself here? Yeah, move 5 to the other side. So it's 5 plus or minus. You know, I don't think I like the 5 there. X plus 1 equals y. So there's your two equations. I might write it a little different. The positive case, let's do the 4/3 x plus 1 plus 5. And then for the negative case, that'd be minus 4/3 x plus 1 plus 5 for the minus case. But there's your two equations. So, like I said, there's a kind of a cheap way to get it, is by setting y equal to 0, or excuse me, setting the right-hand side equal to 0, and then solving for y. It works. Don't ask me to justify it to you. It works. Whew. All right. There's a lot on that one. If you'd like me to go back over something, let me pause for a second and give you a chance to kind of catch up. So if you're following along the steps, it'd be 1, 2, 3, 4, and 5. Yeah. Make that a 6. So that's a 5. All right, there's two more things that I want to share with you and go over with you about these kinds of problems. Now, in general, when we're working with these kinds of things, you're going to get a conic section. So conic sections can all be written like this. This is one of your handouts. What you're going to do a little bit later today is try and decide what the effect of making some of these positive, some of them negative, some of them equal, what all that stuff does. But one way or another, when you work with this graph, you're going to get a conic section. If you work with this equation, I should say. Now, let's look at example F from our handout. And now I'm just going to copy that down onto here. F. So you've got x squared plus 16 equals 4 times y squared plus 2x. And we want to kind of decide, well, what graph are we looking at? And what is this thing? Well, personally, I would start by distributing the 4 You get x squared plus 16 equals 4y squared plus 8y, or excuse me, 8x. And that's an 8, I apologize. Let me move it to the other side where it's going to become negative. X squared minus 8x plus 16 equals 4y squared. There's something special about the left-hand side that maybe you'd notice, maybe you won't. But the left-hand side does have something interesting going on. And you're going to see that interesting thing going on anytime you have something of the form a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. The thing that can attract your attention the most is that the end terms are perfect squares. Both of these. Something squared here, something squared here. The middle term is just 2 times a times b. Now, is it positive? Is it negative? Well, that'll make a difference here. It makes a difference here because each of these are perfect square trinomials. One of them is a plus b squared, the other one is a minus b squared. And that's really a good thing to know about these. So then what? Well, does the left-hand side fit either of these forms? Patty?
If it's the second one, it'll factor into x minus 4 squared.
Perfect. This is x minus 4 squared equals y squared. Now pretend you're solving this on a graphing calculator as opposed to Desmos. You would need to get y by itself. So what would you do to get y by itself here? What would be the first step? All right, you can divide both sides by 4, good. And beyond that, what else are we going to need to do? Because we got a squared here.
Square root.
Yeah, square root. The opposite of squaring is a square root. So on the right-hand side, that means we're going to take plus or minus, or excuse me, on the left-hand side, we're going to take plus or minus the square root. On the right-hand side, we'll just take the square root. You're only going to use 1 plus or minus. So this is going to be plus or minus x minus 4 equals 2y. And you can divide both sides by 2 if you want. So it's going to be plus or minus x minus 4 over 2 equals y. Can anyone tell me what the graph of that's going to look like? So I'll do both. The positive case would be x minus 4 over 2. The negative case would be negative x plus 4 over 2. What's the graph of that going to look like?
One parabola opening up and one parabola opening down.
That's a good try. I appreciate it. It's not a parabola though, because neither one has a squared term. Yeah, they're just lines. Now the interesting thing is, even though we can see their lines here, guess what? Desmos knows that they're lines, because when you graph it, that's all we get, is 2 lines. So what's going on here is that this is a degenerate case of the graph of a conic. Now remember when we talked about conics originally, I said, hey, those are just planes intersecting these 2 cones. If this plane, if you shift it over just enough so that the plane goes through the point of that cone, that's tip, then your intersection is just going to be 2 lines. It's not going to be a parabola, a hyperbola, a circle, or ellipse. It's just going to be 2 lines. And that's what you got. Another case of a degenerate conic would be if the plane went through the tip and only the tip, and then of course you just get 1 point. So, all right, nice. There's one last problem I want to share with you before I get you working, actually maybe 2, before I get you working yourselves in some groups. Let's see. Let's look at example H. So let's pull out example H here. That's this one. It says find the equation for a conic section with the given properties. You got a vertex at -5 and 5 and a directrix at y equal 2. Well, what's a directrix at y equal 2 going to look like? What's a line y equals 2 going to look like? Anyone? Yeah, it's just going to be a horizontal line. All right, so let's take a look at that graph. Let's see, it's right here. I'll shut this one off. Example H, so we got a point here, and this line right here. That's the information that we've got. Well, let me go back and remind you that your parabolas had one of two possible forms. Either this one or this one. Which one of these possible forms am I going to use and fill in information to figure out this graph? The y equals something or the x equals something? Which one does it have to be? The y equals, good. Now someone else tell me the reason for that. Why does it have to be the y equals something, not the x equals something? Anyone? What you got? Yeah, it has to open up, right? Good job. So let's look back at that. It has to open up because if it opened down, then it would open through the directrix. So if you had something, where is it? Yeah, if you had something that opened down, if you had a negative out in front of here and an x squared term, it's going to cross through the directrix. It can't do that. But if it's positive, it has to open up. Great, so it has to be something of this form right here. Y equals a times x minus h squared plus k. Okay. So let's write down some of the things we know. It has to be y equals a times x minus h squared plus k. And there's good news. When you do these problems, you ask yourself, well, what do I know? And there's a couple of these things that you know right away. What things do I know? Julian, do I know anything here yet? Do I know anything about any of these values, a, h, or k?
I know the H is +5, K is up.
All right, yeah, we know the h and the k. So what we're going to get is, this is a times x minus h squared plus k. H is -5 and k is 5. So it's going to look like a times x minus, or x plus 5 squared plus 5 again. Now the only thing left we have to determine is, well, what's a? What is a in this case? And for that, we want to look at, all right, well, we want to look at this relationship. A equals 1/4 times p. So the big question is, what is p? For that, we can look at the graph. Hopefully the graph will help us. Can you tell me what p must be? Yeah.
3.
Gotta vote for 3. How does she get 3?
Oh, the distance.
Yeah, it's just this distance right here, right? The distance of this orange line. That's the distance between 5, 5, or excuse me, -5, 5 and -5, 2. It's the distance between those 2 points. It's just 3. That's your P. So Alright. 1 over 4 times 3 equals 1/12. Beautiful. And that does it. That solves your problem. So y equals 1/12 times x plus 5 squared plus 5 again. Yay. All right. When you do these things, I would always start out by looking at the general form of these problems and saying, which one of these values, these parameters, the A, H, and K, or the A and the B, which one of these parameters can I fill in? Because generally speaking, if they're asking you to kind of reverse engineer things and figure out the equation of something, they're going to be giving you enough information to start filling in some of these, and then some of that information you can fill in the rest of the way by looking at the graph or working with relationships like this. All right, I will help you a little bit with this one, and I want to do one more. I think it's an example like D, not exactly D, but it's like D that I want to work with on. Let's see. Yeah. So while I'm here, let me finish this one a little bit. I would rearrange this a little bit. I'd move the 12y to the other side, and that gives me x squared plus 2x plus 1 on the left-hand side. And when I move this to the other side, what else changes? The sign. Changes sides, changes signs. So that's going to be negative 12y. And I just gave you a hint a little bit about the left-hand side. There's something special about it. Do you know what's special about the left-hand side? Yeah, it's a perfect square trinomial. What would I square to get that? Yeah, thanks, Reagan. X plus 1. And I guess the last thing I would do is divide both sides by negative 12, or multiply by the reciprocal, negative 1/12. And there you go. That's in our nice standard form. Now you can start determining things like the vertex. And for the vertex, start out by saying, well, what makes the square term equal to 0? What value of x would make the square term equal to 0? Negative 1. If I put in negative 1 here, negative 1 plus 1 is 0, squared is still 0, times negative 1/12 is still 0. So you put in negative 1 for the vertex, for x, and you get 0 for y. That's your vertex. And that's where I would start here. A lot of these things aren't going to apply. You're not going to have a length of a major axis or a minor axis because it's not an ellipse. You're not going to have asymptotes because it's not a hyperbola. You are going to have a directrix. All right, but a lot of these things don't apply because it's just not that way.
You're not gonna have more than one vertex for this one.
Exactly. So it's going to be a parabola. By the way, which way is it going to open? Left, right, up, or down? Down. So negative 1 and 0 is going to be right here. Now, if you're asked to graph this on WebAssign and you need to come up with a nice point or something like that, let's see, I'm trying to think if there's something that would be, easy to graph. Boy, I don't want to go all the way out to like negative 9 or something like that. Yeah, I don't think this was particularly easy to graph. Oh, you could set x equal to 0. That's going to be tough because you're going to get a y-intercept at negative 1/12. Yeah, they don't even ask you for that. Maybe an easier point to graph would be if x is 5. So if I put in 5 for x, 5 plus 1 squared is 36. Negative 12 into 36 goes negative 3 times. So that would be an easier point to graph. You're going to have a symmetric point over here, and then you can play, connect the dots. All right, but I'm leaving it to you to find the equation of the directrix and the focus. One last example problem before I give you a little chance to do some work on your own. And then we'll call this one example D prime. I'm not going to give you the exact same numbers I gave you on the handout because I want you to solve this as well. But let's take a look at this equation. 4x squared plus 25y squared minus 40x plus 100y plus 100 equals 0. Now by the end of the day, I want you to be able to look at that and tell me, oh, that's an ellipse. I mean, wow. Really? Yeah, that's an ellipse. You should be able to look at these things and know. The part of that work is understanding what happens with different values of these coefficients. Is one positive, is one negative? Is one of these 0? Either the A is 0 or the C is 0. And then you can look at all these and just know. Those are some easy test questions, is to know, what graph each of these are. But in our case, we got a lot of work to do. And this is the kind of work that you're going to do with example D on your sheet. Now the first thing I'm going to do is pull all the X's and Y's together. And I'll move that 100 over to the right-hand side. Changes sides, changes signs, great. Now, I'm going to factor out the greatest common factor, or the coefficient of the squared term. Now that coefficient is a 4. I'm not factoring out a 4x, I'm factoring out a 4. That's going to leave behind an x squared. If I factored out the 4 from this, what else is it going to leave behind? Negative 10x, good. And leave a little space there for yourself if you want. We're going to do the same thing with our y squared term. I want the coefficient of my y squared term to be a 1. So what should I factor out of this?
25.
25. Thank you, David. If I factor out a 25, that leaves behind a y squared plus what? 4y. And then something else. I'll put that minus 100. That minus 100 is still there. And so here's the thing. I did that so I can do one other little step here. And it's kind of a process that I hinted at right here. I want to make the left-hand side of my graph a bunch of perfect squares. They have to fit this pattern to make them perfect squares. So let me rewrite this. I put a little blank in here. Our job is to figure out, well, what goes in that blank. All right. So it's a two-step process in deciding what goes into that blank. The first step is to take half of that number. So let's do that. It's going to be half of negative 10 is negative 5. The second step is to take that negative 5 and square it. And that gives me 25. Okay. Now that 25 is going to go right here. In fact, I'll put it in green, 25. But wait, I added something to the left-hand side. I also have to add something to the right-hand side to keep things equal. So if I add 25 here, I better not just be putting 25 here. There's got to be something else. 100. Good job. Because really by putting a 25 here, you're putting 4 times 25, or 100, to the left-hand side. Now, you try it. Try completing the square on this part, and then figure out what you're going to add over here. It's that same 2 steps. If you're watching this later, pause the video, give yourself a chance to finish this up. Let's just put a little pause button here. And let me walk around and make sure that people are getting this. So pause. Good. Now clean this up. That cleans up. Each you should clean up. So 3 squares. Be putting the notes online. Okay, so looks like this. You're gonna take half of that leading coefficient, or half of this coefficient, which is 4. Half of 4 is 2. 2 squared is 4. That 4 goes up here. And then 25 times 4 is 100. So we're going to put 100 on the right-hand side. So, yay. All right, looking good. On the right-hand side, negative 100 plus 100 is 0, plus 100 again is 100. On the left-hand side, well, that's 4 times something squared. This is a perfect square now. And the cool thing about it is that these numbers that go in here, you've already got them. It's this one here and this one here. So it's x minus 5 squared and y plus 2 squared. That's looking better. That's looking better. Can anyone tell what graph this is going to be now? Still not there?
Not quite there.
It's an ellipse.
Yes, has to be an ellipse. Well done, David. There's a little bit more work to do to put this in the final form that we want. And let me rewrite this again. 4 times x minus 5 squared plus 25 times y plus 2 squared. What are we used to having on the right-hand side when we graph an ellipse?
1.
A 1.
Ought to be 300, though, right?
No, because that was negative 100.
Oh,
Appreciate it though. If I divide everything through by 100, then I'll have my 1 on the right-hand side. So I'll get a 1. 25 goes into 100 4 times. and then 4 goes into 125 times. There's probably one last thing I want to do just to be able to graph this. What's that one last little step? Anyone?
Take the square root of the denominators.
Yeah, so I'll write it as 5 squared and 2 squared. Excellent. What's the center?
5 and -2.
Excellent. That sounds like Robert. Thank you, sir. 5 and -2. Beautiful. Beautiful. All right. Looking good. Looking good. Now, there is one last thing I'm going to ask that you do, and I'll give you a link for it to play with it. Before I get there, are we okay with what I got here? Yeah, question?
How come you said that example D was prime though?
Oh, it's not the same example D that's in your handout.
Oh,
Yeah, the example D that's in your handout is different. It's the same spirit, but it's just different. Let me see, I don't happen to have that handy, but yeah, here it is. Yeah, the example D that is in your handout is different. What you should do, once you get that into shape, you should also find the foci for both of those. And give the exact equation of the foci. You can do that here, you can graph it. I mean, once you get in this form, you're pretty golden, all right? Now, generally speaking, what I do on an exam is I separate these. I'll give you an equation where I've got all this work done for you and I say graph it. And then a separate problem would be something like, example D, where you're just asked to put it in that form. So the reason I do that is because sometimes people can't do this, but they can graph an ellipse if it's given it in this form. And I want to give you a chance to earn as many points as I can. So, all right. So the last part of this is to try and figure out how is it that I could just look at this and know, well, what equation's coming. And for that, let's see, I'm going to give you a link. And what I want you to do is I want you to play around with different values, different combinations of values of these parameters, A, B, C, D. I had to use F because E is that special constant for us, the base of the natural log. But if you play around with this, well, it looks like you mostly get a graph of a parabola. But what if C wasn't 0? Right now I got I set C equal to 0. So play around with different values and see what happens. Here we've got, hyperbola. Now I've got something that almost looks like a circle. Here it's an ellipse. Well, what predicts what? Well, it's actually very predictable. You just got to go through and play with these things to figure out which branch of this gets labeled yes, which branch gets labeled no. And that'll help you determine which of your 4 conic sections you're looking at. And then afterwards, you can practice with these down here and then finish up the rest of your handout. So, comments or questions on what we're going to be doing? All right, let me give it a wrap here for this one.